Diffraction and interference. So you can see what the inquiry question is that we're trying to investigate. So what evidence supports the classical wave model of light and what predictions can be made using this model. So remember that we've got the two models of light, Newton's particle model and Huygens wave model. And throughout this inquiry question, we're looking at different experimental evidence that supports Huygens wave model. So diffraction and interference are the two main properties of that the particle model can't explain. So we can say that a wave will diffract and interfere, however, a particle won't. So diffraction is just, remember that when we have a wave light that either passes through a narrow slit and the way that it appears to bend and spread out as it passes through that slit or goes around a corner. Interference is when we have the two or more different waves that interfere with each other, so we have a resultant wave that forms from those multiple waves interacting together. So Huygens' principle stated that every point on the wavefront emits a spherical wavelet of the same velocity and wavelength as the original wave. And so from this principle, we know that the waves must spread out from the slits, and this divergence of light is known as diffraction. So how does it work? We've got two significant points that occur when we observe our diffraction pattern. So remember that here we've got a double slit. Okay, so we've got coherent light that's traveling from the left through that double slit, and we observe on our screen on the right hand side here an interference pattern. So we observe a central bright spot in the middle, and then we see alternating dark and bright spots, okay, as we move further away from that central bright spot. So if we just consider the dark spots indicate that destructive interferences occurred. So that occurs when the waves passing from the top and the lower slit are half a wavelength out of phase. So the wave from the bottom here will travel half a wavelength further. They'll constructively interfere on the screen, cancel out each other, and we get a dark spot. On the example on the right, we have constructive interference. Okay, it occurs when we observe the bright spots. So we have that central bright spot in the middle, but then we will get alternating bright spots as we move further away from the central bright spot. And that occurs when the path difference from the light ray traveling from the top slit and the bottom slit is just one wavelength or a multiple of wavelengths out of phase. So then we have crests meeting crests or trough meeting troughs, and we have a bright spot. So let's complete an example where we need to measure the wavelength of a light source after we've shone that laser through our double slit and analysed the diffraction and interference pattern on the screen. So in this case, we've measured the distance between the double slit and the screen as 1.2 meters, and we've measured the distance between the central bright spot and the second order bright spot as 4.5 times 10 to the power of minus 2 meters. On our data sheet, our physics data sheet, we have the path difference formula, which says that d sine theta equals m lambda. So you need to understand what these variables all stand for. In this example, we have the distance between the slits is equal to 0.030 millimeters. We don't know the angle theta. Theta is the angle swept between, if we're at the center of the double slits, and we're looking at the angle when we look up towards the second bright spot, it will be this angle here, theta. We know we've got our second order bright spot, so m is equal to 2, and we don't know what lambda, the wavelength, is equal to. So looking at the right angle triangle here, we'd need to find out what theta is. Okay, we know what the length of the opposite side is, and we know the length of the adjacent side. However, we don't know the hypotenuse, so we can't find the sine of this angle. However, what we do know is that this angle is really, really, really tiny, and that we can approximate the sine of an angle when the angle is really small to be equal to the tan of that angle when the angle is really small. So try that on your calculator. You'll see that sine theta for very, very tiny angles is approximately equal to tan theta. So sine theta for very small angles is approximately equal to tan theta. And tan theta in the diagram to the right is equal to the length of the opposite side divided by the length of the adjacent side. When we assign variables for these two measurements, the length of the opposite and the length of the adjacent sides of that triangle, we say that capital L is equal to the distance between the screen and the double slit, and we say that Y is equal to the distance between the adjacent or between the bright spots. Okay, so tan theta is equal to opposite, so Y over L. And we can substitute this back into our original equation. So instead of d sine theta, we can write it as d tan theta, which is equal to d times y over L. And we know that this is equal to m times lambda from our path difference formula. Now we have an equation where we know m, in this case, is 2 because it's a second order bright spot. We're trying to find lambda. We know the distance between the slits. We know the distance between the central bright spot and the second order bright spot. And we know the distance between the slits and the screen. So we're just going to substitute our known values in there. So because we're trying to find lambda, we'll rearrange the equation to make lambda the subject. Then substitute the known values in, so d, and ensure that your measurements are in SI units. So for lengths, they should be in meters. So d is the distance between the slits, so 0.030 millimeters. So divide by 1,000 to convert to meters. Y is our measurement between our distance between the central order bright spot and the second order bright spot. So 4.5 times 10 to the power of minus 2. Because it's between the central and the second order, m is equal to 2, and our L is 1.2 meters. Entering that into the calculator gives us 5.6 times 10 to the power of minus 7 meters. When dealing with wavelengths of light, it's really handy to give your answer in nanometers. So remember that 1 nanometer is equal to 1 times 10 to the power of minus 9 meters. So if we divide this answer by 1 times 10 to the power of minus 9, we'll convert our answer to nanometers, and that will give us 560 nanometers. It's really handy to remember what the range is for the wavelengths of visible light. They range from 400 to 700 nanometers, and 700 nanometers is our longer wavelength, so that is in the red part of the visible spectrum, and the 400 nanometers is the shortest, so the most highest energy visible light, and that is around our violet or blue end of our visible light spectrum. So let's practice another example. In this case, we've got light of a specific wavelength, 430 nanometers, falls on a double slit whose separation is 4 times 10 to the power minus 4 meters. Calculate the angular distance between the central bright band and the second order bright band on one side of the interference pattern. It's always handy to sketch it on a diagram, so we're trying to find this angle here, knowing that this is our central bright spot here, or band just here, where m equals 0. This is our first order bright spot on one side of the central bright band, and this is our second order, where m equals 2. They're not actually equally spaced like they appear to be in this diagram. So writing down the data that we do know, we know the wavelength lambda, and we know the distance between the double slits, and we know that we're trying to find theta for the second order bright spot, so where m equals 2. You'll notice in this example we don't need to know L, which is the distance between the slit and the screen, and we don't need to know, or we haven't got the data for, the distance between the central bright spot and the second order bright spot. So we can just use our normal double slit experiment formula from the data sheet, which says that d sine theta equals m lambda. Write down the equation and rearrange to make sine theta the subject. Then substitute your known values in. So we've got m equals 2, wavelength of light, and the distance between the slits. And then don't forget to find the inverse sine to find the actual angle. Rounding our answer to 2 sig figs gets us 0.12 degrees. In the next example, we've got a double slit of known separation, We've got our known wavelength of light that is being shone through the double slits, and we're trying to calculate the distance from the central bright band to the fifth bright band on one side of the screen, and we know the distance from the double slit to the screen. So again, sketch the diagram. So if this is our central bright band, in this case we're trying to find the linear distance, so the distance from the central bright band up here to the fifth bright band, and that is the value that we call, or the variable we assigned for that distance is y. So we know d, the distance between the double slits, we know the wavelength of light lambda, we know the distance between the double slits and the screen, we know our order of our bright spot is m, and we're trying to find y. So in this case we can't just use our double slit formula because we don't know theta and it doesn't have our L in it or our Y. So we need to do our approximation for tan theta. So approximation is that tan theta equals Y over L, which is this dimensions here, Y over L, and that for very, very small angles, that's approximately equal to sine theta. So we can now substitute that into our double slit experiment formula, and then arrange to make, we're trying to find this time y, so let's rearrange to make y the subject. So y is going to be equal to m times lambda times by L divided by d. Substitute our known values in, so 5 times our wavelength times the distance between the screen and the slits, divide by the distance between the double slits, making sure that it's all in meters, so our SI units. Entering that into our calculator gets an answer of 5.0 times 10 to the power minus 2 meters, so about 5.4 centimeters. So the distance between our central bright spot and our fifth order bright spot on one side of the interference pattern is about 5.40 centimeters. Now, diffraction gratings are just a slight variation of our double slit, where we have something that's made of glass, perhaps, that's quite transparent, which is transparent, with lots of different etchings or scratches on it. So the gap between these scratches, or each gap just functions as a slit. Okay, so they contain a large number of slits, similar to double slit, except diffraction pattern, except the maxima, so the bright spots are much more distinct. It's handy to be able to determine, well, you need to be able to determine the distance between the slits. Okay, there's regular spaces between them of equal length. Okay, and to determine the number of lines per meter, you just get 1 meter divided by the number of lines. Okay, so if a diffraction grating, for example, has 5,000 lines per meter, calculate the distance between the slits. D is equal to 1 divided by 5,000, which gets you 2 times 10 to the power minus 4 meters. We still use the same path difference formula from our data sheet, and we can still use our substitution here of, this should say Y, over L for our approximation for sine theta. So if we start with our first example, we've got a diffraction grating ruled with 2,000 lines to the centimeter. It's used to find the wavelength of monochromatic light. And when the beam of this light is shone normally, so at right angles onto the grating, the angular distance of the fifth bright line from the central line is 28.7 degrees. Calculate the wavelength of light. So firstly, sketch diagram. So if we sketch where the diffraction grating is and the screen, and then draw in our normal, so a line measured at right angles from the center of these two particular, or from the center of the diffraction grating to the screen. And we know the central bright spot will be in the center there, and we know the angular distance to the fifth bright line. So here's our central bright spot, and here's our first order, second order, third, fourth, and fifth order bright spot, and the angular swept between the normal and the line that joins the center of the diffraction grating to the fifth bright spot is 28.7 degrees. We're trying to find lambda. So we firstly need to find the distance between each pair of slits on the diffraction grating. So we need it in number of slits per meter. So we get our measurement of 1 meter, okay, divided by the number of slits in 1 meter. In the data given, we had 2,000 slits for every 1 centimetre, which is 0.01 metre. So the distance between each pair of slits on the diffraction grating is 5 times 10 to the power of minus 6 metres. Now writing down what we know that m equals 5, we know our theta equals 28.7 degrees, and we're trying to find lambda. So we can just use our path difference formula, which says that d sine theta equals m times lambda. Rearrange to find lambda, divide both sides by m, and substitute our values in. So we have 5.00 times 10 to the power of minus 6 times the sine of the angle, make sure your calculator's in degrees, and divide by the order of the bright spot, which is 5. So our answer is 4.8 times 10 to the power of minus 7 metres, but remember it's handy to answer in nanometres. So dividing that by 1 times 10 to the power of minus 9 gives us 480 nanometres.